Hi, Miss Millender here, and today we're going to do some more calculating with gas laws. But today we'll be looking at Charles's law, which is V1 over T1 equals V2 over T2. Same arrangement though, in that the ones are the measurements before an event and the twos are the measurements after an event. A student made this up last year. I thought it was very clever. Charles lives in Vermont. So VT, Charles lives in Vermont. It doesn't really, but people were wondering how to keep Charles and Boyle's law separated and whose is which ones. And so I thought that was a cute way to remember. Okay, so here he is, Jacques Charles, who is another interesting guy. You can read all about it, but he's the one that came up with this calculation. All right, so here we have a little demonstration. It's a little GIF. So what's happening here? The added heat increases the temperature of the gas. The particles then move faster and pressure increases momentarily. Well, why is it momentary? Why doesn't it just increase? The increased pressure pushes on the flexible container, increasing the volume, therefore decreasing the pressure, until the pressure in and the pressure out are the same again. Right? And you can see the relationship up in the graph. As the temperature goes up, the volume also goes up. All right, so Charles's law, however, is only true if you're in a flexible closed container, again, just like the other. So as the temperature increases, the volume must increase as well. The thing you have to remember, though, is like Boyle's law, Charles's law is only true under certain conditions, and in this case, you have to assume that the mass and pressure remain constant. Because if you start messing with the mass and the pressure, then the math gets a whole lot more complicated. So here we are back to reviewing what you need to show in order to get full credit on any calculation. The first thing is you need to show the formula. But just like in Boyle's law, the formula needs to be manipulated so that the unknown variable is by itself on the left-hand side of the equation. And we'll do an example with that in a minute. You have to substitute your numbers in for the variables, including the units, and then your answer needs to have the correct units and sig figs. So let's go on and do an example. So just let's manipulate this formula first. So here we have Charles's law, and I want you to solve for V1, let's say. So here we have V1 in the numerator and T1 in the denominator. Now you could multiply both sides by T1 and it would work. However, if you're trying to solve for V2, it gets a little trickier. So here's the way that I highly recommend you approach this manipulation, because this way you're significantly less likely to make a mistake. You're going to start by cross multiplying, because you want to get rid of the fractions, because the fractions are what make manipulating the formula a little bit trickier. So we have V1 T2, T1 V2, and now it's a simple matter of dividing by the thing you want to move. So we're trying to get V1 by itself, so we're going to divide both sides by T2, they cancel, and you're left with V1 equals T1 V2 over T2. So I highly recommend that you always start manipulating Charles' law by doing the cross multiplying. And for now, you have to show this manipulation. Later on, you won't have to, but for now you do, just so I can see that you know what you're doing. All right, so here we have a practice problem again. I'm going to read through it, get a sense of the story. A balloon holds 4.5 liters of helium at 23 degrees Celsius. The balloon is then put into a cold van for delivery. Okay, so it's a balloon delivery. The balloon and the helium drop to a temperature of -3 degrees Celsius while it's out in the van. Yikes. How big is the balloon now? So what would you anticipate happening if the balloon and the air inside get colder? I would predict that they would get smaller, but let's just see. So now I'm going to identify all my numbers and my question, how big? And so 4.5 liters is the initial volume. 23 degrees Celsius is the initial temperature. -3 degrees Celsius is the temperature after an event, and in this case the event is them getting put in a cold space. And how big is the second volume. All right, so we know we have volumes and temperatures, so we're going to use Charles's law. So we start here. So the first thing we're going to do is manipulate the formula so that the unknown is by itself on the left. You are required to do this part. So I'm going to start by cross multiplying. Then I want V2 by itself, so I'm going to divide each side by T1. Then I'm just going to flip the equation so I can get the V2 by itself. And there we are. So that's the formula we're going to start with. Now, do not write this next part in your composition notebook. I need to show you something, but I'm afraid if you put it in your notebook, it'll make you confused. So you can write it down if you want, but I don't recommend it. So let's go. So you're starting with the manipulated formula. Now you have to substitute your numbers. So you go up and you look in the word problem. V1 is the 4.5 liters. T2 is the -3 degrees Celsius. T1 is 23 degrees Celsius. Now let me tell you, one of the most common places where blunders occur when using Charles's law to calculate is flipping the temperatures, putting the T1 on the top and putting the T2 on the bottom. Just be careful, right? So we plug this into the calculator. Oh, sorry, I did it again. We're going to cancel the C's. We plug this into the calculator. This is what we get for an answer. Look back at the sig figs, 2, 2, and 3. So we're going to have 2 in our answer. And there it is, -0.59 liters. Math worked. Everything's great. Let's just go to the next page so we have some room. Okay, so this is what we had on the other page. Looking at the answer you just got, there's something very strange about that answer. Look at what you're calculating. Look at what you're looking for. And is it even possible to have a negative volume? Like, what would that be? It's less than nothing. It's impossible. So you can't have a negative volume. And then, what would happen if T1 was 0 degrees Celsius? Can you divide by 0? No, and that just causes a big giant mess. So something has to change, because you have this possibility of getting a negative answer, which we don't want. So earlier in the year, what did we discuss? What measurement system has no negative numbers? Do you remember? You'll see in just a second, because always, 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 always use Kelvin. You have to use, the temperature has to be in Kelvin. Always, 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 always. No exception to the rule. It's the way it is. So now you can start writing again. So this is the right way to do it. So let's do a couple practices. Converting to and from Kelvin, you have these two formulas. They're on your formula sheet. You will always have access to them. Sometimes people have a difficult time reading these, so let me just go through it for everyone. TK means I want to find the temperature in Kelvin. So TK, you're looking for Kelvin, so you take your Celsius and you add 273.16. To get the temperature in degrees Celsius, which is the next equation over, you take what you have for temperature in Kelvin and you subtract 273.16. Does anybody remember where that number 273.16 comes from? That's the temperature of absolute zero in degrees Celsius. So that's how we're getting back and forth within these two measurement scales. All right, so let's say we have room temperature. It's in degrees Celsius. We want it in Kelvin. There's no degree with Kelvin. So we want it in Kelvin. So I take the Kelvin formula. I want temperature in Kelvin, so I have to take the temperature in degrees Celsius and add 273.16. So sure enough, I do that. I do my addition, but I just added, so what's the sig fig rule? The place value of the least precise first best guess. So that's the 0 in the tenths place. So I have to round this to the tenths place, and I get 296.2 Kelvin. Great. Let's do one where you put it back into degrees Celsius from Kelvin. So let's take the boiling point of liquid nitrogen. So that's the really cold stuff. Boiling point means it's at the point where it's converting from a liquid to a gas. Okay, so we take that formula where we're looking for the temperature in degrees Celsius. We plug in our numbers, 77 minus 273.16. Plug it into the calculator, we get negative 196.16. But wait a minute, didn't we just say you couldn't have negative numbers? Well, yes. What you can't have are negative numbers in Kelvin. You can have negative numbers in degrees Celsius. So anyway, we look back, we see that 77 goes out to the ones place, 273.16 goes out to the hundredths. We're going to round to the ones. So our answer is negative 196 degrees Celsius. So that's how you use those formulas. So now let's go back to our original equation. Before you plug anything into any formula, what do you need to do? Hopefully you said get those temperatures into Kelvin. So we're going to take this formula, TK1. Now, temperature in Kelvin, this goes for temperature 1, right? So that's why it has that extra subscript. We take what we have, 23 degrees Celsius, plug it into the calculator, round to sig figs. So now we know that T1 is 296.2 Kelvin. But we have two temperatures, so we have to do it again. We have the formula. We have negative 3 degrees Celsius but plus 273.16. We add them up. We look back for sig figs. And so the temperature in Kelvin for T2 is 270.2 Kelvin. Now that our numbers are in Kelvin, we can proceed. So I just transferred those numbers we just calculated over to here. Here's the formula we manipulated earlier, and now it's time to do the substitutions. Notice I'm substituting the Kelvin temperatures in for the T1 and the T2. I cross out the Kelvin. I get that for my answer. I look back, try to figure out sig figs. It looks like it should be 2, so 4.1 liters. Again, I want you to be critical about your answer. Does the answer make sense? So we go back to the problem. We had a balloon at 4.5 liters, and it got put out in the cold. So the cold is going to slow down the particles. It's going to be fewer collisions, less pressure, and so the volume of the balloon is going to go down. Does 4.1 indicate a smaller volume than you started with? Yes, so it seems reasonable. That seems like a reasonable answer. So, great, you should be confident about that. So these calculations are a little bit more complex than the Boyle's Law one. So I need you to keep your notes open when you're working on the practice problems. And bring any questions to class, and thanks for listening.